Thank you very much. All right. Calc 2 slash IPX Calc lecture. Oh, is that visible? That's good. We are recording. That's all good. All right. So the next thing we have two major topics to talk about today. One leads into the other. The first thing that we're talking about is, of course, power series. What is a power series? What information do we need to know about a power series? So, as we know from a Taylor series is a summation from n equals 0 to infinity. This is Taylor. I'm just writing it a little bit smaller up here just to fill up this little space. Of the nth derivative at a over n factorial times x minus a to the nth power. And all intents and purposes, this is what we refer to as one of the important power series. And a power series is a series that can be written as some function of n, so c of n just standing for some function of n, times x minus a to the nth power. And in this case, this c sub n right here would be your the nth derivative at a over n factorial coming from the Taylor. So, and talking about these power series, we'll expand on this name of the power series. But the question we have is, for what values of x does the power series converge? And that's going to be the first question that we are going to answer. So, now, the most common power series is something that is geometric. This is where we took in regards to the ratio test. We have that series, and we can take it for, i.e., from n equals 0 to infinity of just x to the n. A nice plain power series. This is a power series for where c sub n is just 1, a constant, all right? And we're centering this at x equals 0. And it turns out that this is the Maclaurin series, of f of x equals 1 over 1 minus x. I don't have to say where it's centered. Because, of course, when I say Maclaurin, that means it's centered at x equals 0. And we know that this series, because of this fact that this series is what it is, we know that the absolute value of x, it converges for the absolute value of x being less than 1. So that one's nice and straightforward in regards to what it converges. And we're just making the connections to both a geometric series and this. And if you think about it, as long as x is less than -1, then that, the 1 over 1 minus x represents the sum of that geometric series. So the sum of the geometric series is the series, because that's what it's supposed to be. So what I'm trying to show you here is that when we say what is the sum, when it's a function, we relate it to some known function f of x. And so because the sum of the infinite geometric series, x to the n, is 1 over 1 minus x, we can go from here to here that they're equivalent. And of course, we can actually do that long way, and that's going to lead us into our next pieces as well. So we're going to expand on this idea right here. Now, something to know, note that the series of x minus a to the n always converges at x equals a. So in the case of the one on top, a is 0. So, of course, 0 to the n is what it would converge to. So that's kind of like saying, what is the summation when the radius is equal to 0, and you would just get 1 in that case. So you get a sum. It is just going to be 0 plus 0 plus 0 plus 0, and so forth. And so it does, in fact, converge at that value, always. So that's just something to know. It always will converge. And that just means that it's true, that this function and this summation are equivalent to each other as so long, and in this case, as x is less than 1, the absolute value of x. If the absolute value of x is not less than 1, then these two things right here are not equivalent. It wouldn't work because, of course, a geometric series, if the absolute value of x was not less than 1, then it would it would not converge to 1 over 1 minus x. The sum would diverge. Ratio test. We know from the ratio test, and so in doing this, x is just an unknown constant. Okay? For the following limit. That the limit, let me change the color here. The limit as n approaches infinity, this is using the ratio test right here, of the absolute value of c sub n plus 1 times x minus a to the n plus 1. That's just me, remember, the nth term, the nth plus 1 term over c sub n, x minus a to the n. We know that this must be less than 1. So we're taking a power series. Remember, we're just taking the knowledge over here that this is the power series and how it's written. And we know that this power series will converge as long, from the ratio test, as long as this piece here is true. Just to help us clean this piece up real quick, we'll state that c of n plus 1 over c sub n, we're just going to call that p sub n, because it's just going to be a new function of n. Then we have the limit as n approaches infinity of the absolute value of p sub n times x minus a. And the reason why it's x minus a is because n plus 1 terms over n terms cancel out with the n terms, the n powers, is less than 1. Which gives us that the absolute value of x minus a times the limit as n approaches infinity of the absolute value of p of n must be less than 1. Now, the purpose of, well, something to note from here, this is also showing that this will converge at x equals a, because if x is equal to a, then of course we're going to get 0, which is going to give you less than 1. If x was a, you would apply it before the actual limit, so you would get 0 times a limit, which is going to give you 0 in that case. Well, it's a little bit shaky, but that's the best way to kind of just put it shorthand. So really, we have to look at this piece right in here. We have to look at here. And I know, and I will make the connection to probably what it looks a little bit more traditional in terms of just the normal work. But what we get is we get 3 different scenarios. All right, we get scenario 1, the limit as n approaches infinity of the absolute value of p sub n. It turns out to just be 0. And we know 0, of course, is less than 1. in this case, no matter the value of x, the power series converges. Okay. We have some special names of this that we need to take into account. We say, therefore, that the interval of convergence is what? So for those of you who have taken it. No. All real numbers is an appropriate way to say it. If you, I like to use interval notation. Yeah, so negative, infinity, infinity. Or you can just say all real numbers. Okay. And the radius of convergence is just a piece of saying how far out from x equals a can you step away from that and still get a function or a sum for this geometric power series. In that case, it would be just infinity. So we call that the radius of convergence is infinity. And like I noted, this is how far from x equals a you can step away. Okay. We'll do a quick example of this in just a little bit as well. So that's scenario one. When you take the limit of whatever the n's are. Remember, anything that's not an n, because you're taking the limit as n goes to infinity, anything that is not an n, you can treat as a constant and just pull it out. And when we take this limit of this ratio test of this power series, if it just gives you 0, so you get something like a constant over n, and then you take the limit as n goes to infinity, or you might get something oftentimes like a factorials that cancel each other out, reduce. Whatever it happens, the growth rate of the denominator is higher than the growth rate of the numerator, and so that nth term, that piece of n, goes to 0. It'll converge for whatever values that we have. Scenario 2. The limit, let's zoom back in here. The limit as n approaches infinity of the absolute value of p sub n equals infinity. Well, we know that that's equal. Infinity is less than or equal to, less than or greater than 1. It's greater than 1. So no matter the value of x, except, of course, except x equals a, the power series diverges. So the interval, I'm just going to write as shorthanded, the interval of convergence would be just A. And we designate just A as a brace. The only value that will work for the convergence is at x equals A. Yes?
Wouldn't it, like, in indefinite form of 0 times?
So, and this is what I'm saying. It just kind of comes back from the initial definition of what happens over. Because if we're centering this at x equals a, then you're just going to get 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, which is a convergence. It's going to converge. So if you're going to just get 0 plus 0 plus 0 plus 0 plus 0 when x is equal to a. And the radius is 0. And then we have scenario 3, the fun one. The fun one. This is when the limit as x approaches infinity of the absolute value of p sub n is equal to some value p. And for this, I'm going to spend a little bit more. I'm going to go on to the next page. Yes, it is. I need a little bit more space, so I'm gonna write this down over here. Okay, so we get some constant P. Okay, does everybody follow that right here? Anybody need a little bit more space and time for writing that? No, okay. All right. So, if this is true, if the limit as n approaches infinity of the absolute value of P sub n is equal to P, then the absolute value of x minus a times P must be less than 1, which means that the absolute value of x minus a must be less than 1 over P. And so it turns out, and I'm going to show you, there's another way of doing this, but this is the radius of convergence. You can also just determine the radial convergence. The radius of convergence is also just half of the interval of convergence, half the distance of the interval of convergence, right? And that's typically how most students will calculate the radius of convergence. If it's going from like -2 to 6 or whatever, that's a distance of 8. So the radius of convergence would be half of that, which is 4. That's mostly the typical way that you can just get about it. But this is why that radius of convergence, why it would be 4, because you're going to have this piece right in here. Now, we need to solve an algebraic equation of the absolute value of x minus a is less than 1 over p, which, if you remember from your algebra days, solving inequalities of absolute values gives me that x minus a must be, okay, we'll do it over here. X minus a must be less than 1 over p, and x minus a must be greater than -1 over p. Okay. So when we solve this equation, we're going to get, so here is a. This is going to be a minus 1 over p from solving that. This is going to give me a plus 1 over p from solving that. And we're going to get some interval that's going to go from here to here. Now, the reason why I'm using dashes in here is because, as we must remember, the ratio test is inconclusive at the endpoint, because it's not less than or equal to. So when the absolute value of x minus a equals 1 over a, well, that would be the same thing as starting from here. If we started from here and we said the absolute value of x minus a times p is equal to 1, that's what's going to give me these endpoint solutions right here. And the ratio test is inconclusive at those endpoints. And so we don't know if it's closed and an open. We don't know if it's two opens. We don't know if it's two closed. We don't know which endpoints from the ratio test. But we do know the interval of convergence, right? Or we do know at least the radius of convergence at this point. We have not confirmed the interval of convergence. And so what we must do, it's like a whole new problem, 2 new problems. We must test the infinite series. This is based on our last lecture, our last 2 lectures, the infinite series at both endpoints. Okay. And so what literally what you're going to do is when you're going to get some actual value, like you're going to get x equals -2 and x equals 4, or something like that. So those would be your endpoints. If you're going from -2 to 4 as your interval, then you would take x equals -2 and plug it into your original power series, which is going to give you what looks like something from our last lecture. There's no x's anymore. It's just going to be some series of n. It could be geometric. Most likely it's going to be geometric. It could be, but it could be something that you have to use an integral test for, a direct comparison test. You have to prove it using proper techniques. Prove convergence / divergence using proper techniques. Okay? So, you're going to, basically the best way to do it is you're going to test x equals a minus 1 over p, and you're going to plug this into your original, our original power series, the sum of c sub n times x minus a to the n. You're going to plug in that value right in there, and then you're also going to test x equals a plus 1 over p, where once again you're going to plug that into your original power series of c sub n times x minus a to the n. And you must, once again, you are using those techniques that we had in our previous one. You're plugging that in, and then you have to go through your checklist. Nth term test, alternating series test, geometric series test, telescoping, comparison test, all of those various ones. And then based on those, then you can determine, is it like bracket, bracket, it converges at both, bracket, parentheses, 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 parenthesis, bracket. You would determine that based on what you have here. But you must prove it correctly. All right, we have 11:05. I know there's probably some good questions that are coming in here. I want you to be able to, sit on this for just like 5 minutes, because so we have this idea of a general power series that we just talked about, which is that it's some function of x gives me some series, c sub n, times x minus a to the n. This is the general, what we call just a general power series by any definition. But we also have what is known as a Taylor series, centered at x equals a, which is specifically the series from n equals 0 to infinity of the nth derivative at a over n factorial times x minus a to the n. And so these, a lot of this is just kind of like trying to go in reverse and starting to think about things in, the vocabulary that is used is, function to Taylor series or power series is a Taylor series of a function. So you can think of it, but not necessarily all power series are technically going to be so I guess you could say all Taylors are power, but not all power are Taylors of some specific function. That's the more appropriate way of saying it. And what we're going to be doing, and I think all we're going to be able to cover in this course is this summer, is the Maclaurin series, or of course x equals 0. So I made a connection in the prior lecture, and so let's review what we did earlier on in the summer, or not early on, probably, what was it, last week, for the example of f of x equals 1 over 1 minus x, okay? Well, if we want to find the general series, we know that we can go through the long process, right? The process that we know. So we found what we did, and this is what we did in our lecture, f prime of x is 1 over 1 minus x squared. F double prime of x was negative 2 over 1 minus x cubed. The third derivative at x was 3 factorial over 1 minus x to the fourth. This gave me that f of 0 was 1, f prime of 0, which is, of course, 0 factorial, was 1, which is, of course, 1 factorial. F double prime of 0 is 2 factorial. The third derivative at 0 is 3 factorial. And so we can, induce that the nth derivative at 0 is going to give me what? Oh, so there's a 3 here. That's why it's probably there. Now that should be clear. It is n factorial. So we can write this, and we can see that this is going to give me 1 plus x plus 2 factorial over 2 factorial x squared plus 3 factorial over 3 factorial x to the third plus dot, 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 plus n factorial over n factorial x to the n. And that our function, 1 over 1 minus x, is equivalent to this, which is just the same way of saying that 1 over 1 minus x can be rewritten as the known power series or known Maclaurin series of the summation from n equals 0 to infinity of x to the n. Because all these x is cancels and cancels and cancels and cancels and cancels. We refer to this, and so this is one of our known, this is now classified for us as a known Maclaurin series. Which needs to be memorized. I'm not putting like memorized. Okay? This is the first of our known Maclaurin series. That this is one of those power series that specifically matches to the Taylor, the Maclaurin series of 1 over 1 minus x. And so that they are equivalent for each other. And what something also known as this is only true when the absolute value of x is less than 1. And so this function, if I graphed 1 over 1 minus x, after at x equals 1, it's going to kind of just blow up. And of course, at x equals -1, you're going to get like what, 2. So at those values, the sum and the actual function are going to diverge from each other. They're not going to be perfectly overlapping and matching. And this is something that's very helpful in higher order mathematics, is because you might be working with some function and trying to do some work with a function that just the math doesn't work, or you're having a hard time figuring your way out for doing a solution to that function that you're working with. And so what you can do is you can rewrite this function as an infinite series. And of course, you don't want to go through this whole process as such. You don't want to have to go through this entire process to figure out what that power series is going to be. So we can just write the two and have it, and boom, you have that. And then you can do the mathematics to that series. And from there, you can convert back, or you can find out what your solution is going to be. Now, something to note here that's going to help us for the next piece. So please note, a Maclaurin series of a polynomial is just going to give us the polynomial. That's it, to the nth power. So what I'm trying to say here is that if f of x was equal to x cubed, and we would try to go through this entire process all over again, you would just get 0, because that's the first one, plus 0, plus 0, plus 3 factorial over 3 factorial x cubed. Then it's going to be plus 0, plus 0, plus 0. And so all we get is that x cubed. When I center it at x equals 0, we're going to get the same thing. And so if you center it at like x equals 1, and you're going to have x minus 1, and this plus x minus 1. If you were to expand that, that Taylor series to the nth power, because it's going to be 0, after a certain time, it's just going to be 0, 0, 0. If you were to expand it, everything else that is not the original polynomial is going to cancel each other out, and you would get just your original polynomial. And so the Taylor of a polynomial is just the equivalent of that polynomial. Does that make sense? And because of that property, we can do some pretty cool stuff. That where we don't have to do that whole process that we find the first derivative, find a second, find a third, plug it in. You don't want to have to do product rule. And sometimes product and product rule or quotient rule, your derivatives can be very tough. And then you have to make that connection. All right, after doing all that, what is the general term for that Taylor or Maclaurin series that I just created? It can be very, pages of work to do. But if we know these two facts of a known Maclaurin series and that the Taylor of the Maclaurin of a polynomial is just that polynomial, we can utilize some nice mathematics. 1 over 1 minus u would just be the sum from n equals 0 to infinity of u to the n, all right, where u is some polynomial. Because if u is a polynomial, once again, that expansion is just going to give you back that little piece, or it's going to give you back exactly what you had on beforehand. So this is just I like to write it with the terms of u, but this is something that both of these two things now allow us to do, knowing that 1 over 1 minus x is just the summation of x to the n, then the sum n of a polynomial, then we can utilize this new property. So let's do an example of how we can manipulate. This is manipulate of known Maclaurin series. Sorry about that. Missed that little headline. But let's do an example. Let's look at f of x equals 1 over 1 plus x squared. And we want to, find the first 4 non-zero, non-zero terms. So this is a little bit tougher than that one, right? And 2, we want to find the general series. Okay. Now, we could find the first, take the function, plug in 0, find the derivative, plug in 0, take in derivative, plug in 0, and so forth. But those derivatives get very ugly very fast, right? This derivative, not too bad, chain rule. The next derivative, quotient, or some chain rule mixed with the product rule. And then you have to do multiple ones on the next one. It gets really ugly really, really fast. But we can use the property that we just, that would be that's the long way. And if I ask you this, or when I ask you this question on the final, you're not meant to try to find the first derivative, second derivative, third derivative of f of x. You're going to look at this and say, oh, this looks like 1 over 1 minus u. And so you're going to note that, oh, this is the same thing as f of x equals 1 over 1 minus negative x squared. And so my u is negative x squared, which is a polynomial. And so we can just plug it in, because the manipulation of a Taylor of a polynomial is just a polynomial, and therefore it's not going to change the mathematics. So we know that 1 over 1 minus x is 1 plus x squared plus x cubed plus dot, 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 plus x to the n. That's what we just learned. that's something that now goes into our memorization bank. Therefore, 1 over 1 minus negative x squared, which is, of course, 1 over 1 plus x squared, is going to give me 1 plus negative x squared plus negative x squared, and I'm just going to, I'll stop doing that, plus negative x squared to the third, plus dot, 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 the quantity plus negative x squared to the nth power, which gives me 1 minus x squared plus x to the fourth minus x to the sixth plus dot, 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 plus negative 1 to the n times x to the 2n. And so 1 over 1 plus x squared, if I were to find the Taylor polynomial, or the Maclaurin polynomial, Taylor series, sorry, would be this series from n equals 0 to infinity of negative 1 to the n, x to the 2n. Now, we don't have enough time to do a lot of other stuff, but there's a couple of nice things that we can recognize a few things from here. And one, what type of series is this? It's alternating. So we can now approximate it very well and also know how far our approximation is for this function. Another thing I can really recognize in here is I can answer secondary question here. So secondary questions could be, it's an alternate series error. I can now ask you that because it's an alternating series. I can also ask you the value of f, the kth derivative at 0. I can also ask you what is that one. And we can recognize this right away. What is the first derivative? What is f prime of 0 in this place? What is f prime of 0? Do you see a linear term? Do you see a linear term? No, there's no linear term. So for example here, f prime of 0 has to be 0 because there is no term in here. And so if you did the work out, you can find 1 over 1 plus x squared, find the derivative, plug in 0, and you're just going to get 0. We can also see that f prime of 0, f double prime of 0 is going to be equal to, well, we know that f double prime of 0 over 2 factorial is equal to negative 1. So f double prime of 0 equals negative 2. You can also determine now things like max min at x equals 0. Okay, well, do we have a maximum or do we have a minimum at x equals 0? This has come from, technically that's something that I did in this course, but it's something that you did in Calc AB, our initial ones. The first derivative is 0. It's concave down, so we know that we have a horizontal tangent and concave down, which means it's a maximum. Yes?
When you were getting the values earlier, like 0, -1, what were you plugging in to get those? Like, what were you looking at to find those values?
The 0, this right here? Or,
F prime of 0 equals 0, and that's double prime of 0.
so if I were to do the work the long way, it would be, f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared. And so that's kind of where I said, so to get to this value right here, I would have to do, plus f double prime of 0 over 2 factorial, and it would have gotten me negative 1. And that's how, because if I did it the long way, that is the coefficient for the quadratic term in the Maclaurin series, which is calculated by finding f double prime of 0 because it's always centered at 0. We don't know what at 1 or 2 or 3 is, over 2 factorial. Yes?
So, I understand the second part, but if you have like f prime is 0 for the first one, how, like, why would it not be 0? Like, why is it 1 if you're multiplying?
F prime of 0 is 0. Oh, it's because it's f of 0, because remember the connection here is that basically, so it sounds like you wanted me to write this a little bit more. This would be f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared. So zooming in on here real quick, which is here. So there's technically imaginary plus 0x. That's right there. So if you were doing this the long way of finding all the derivatives and making the Maclaurin series and writing them all out, the first few terms, you would have gotten 0 times x. And then you would take the derivative of that function and you would have gotten 2 factorial. And so when writing the next term in the quadratic approximation, right, it'd be 2 factorial over negative 2 factorial, over 2 factorial times x squared. If I wanted the third degree or the second degree Taylor polynomial. All right? But you don't have to go through all that work. You don't have to find a derivative. If we know it and all we're doing is manipulating it with a substitution of a known polynomial. Okay? A polynomial times a polynomial gives us a polynomial. And the same thing happens, therefore, with the series of it. If we have a summation of a polynomial and we multiply it by the polynomial, then we can just combine those two, just like I just did right now. And with an example of this one is, let's look at f of x equals 2x over 1 plus x squared, right? This is therefore 2x times 1 over 1 plus x squared, right? Now, 2x is a polynomial, but it's also its own Maclaurin series, centered at x equals 0. And the other one we're going to find is centered at x equals 0. So they're both centered at x equals 0. So if I were to do the Taylor expansion, then we're going to get 2x. That's the Maclaurin expansion of 2x. 2x is its own Maclaurin expansion. It is a polynomial. Times 1 minus x squared plus x to the 4th plus x to the 6th plus dot, 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 plus negative 1 to the n times x to the 2n, right? And so I can now just multiply. And doing so would give me my first term being 2x minus 2x cubed plus 2x to the 5th minus 2x to the 7th plus dot, 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 plus negative 1 to the n times 2x to the 2n plus 1. And what we've just found is that 2x over 1 plus x squared is the same thing as this, or these would be the first terms, as the summation from n equals 0 to infinity of negative 1 to the n times 2, or you can say negative 2 to the n, right? Or times 2 x to the 2n plus 1. And again, so we were able to figure this information out not by having to go through the first derivative, second derivative. Like you could do all the calculus, work, and you would find that f of 0 turns out to be, that's easy, we can calculate that. It's going to give me 0, right? If I plug in 0, 2 times 0 over 1 plus 0 squared, f prime of 0 would give me 2. F double prime of 0 would give me 0. The third derivative at 0 would give me Well, we know that this over 3 factorial is equal to negative 2. So the third derivative at 0 would have given me negative 12. But you'd have to go through figuring out all the derivatives in order to get to that spot. We don't have to do that. And what we found out is now we can work with this. So if you have this ugly function here, you can understand that the properties are going to be the same as this right here. Questions to that? Okay. If you want to expand, you can also do an expansion of Taylor polynomials or Maclaurin polynomials when they're still centered at the same value. And you can once again multiply the terms of the power series, and it will be still true. So another way of doing, I'm going to show you this problem in another way in a little real quickly. So let's look at f of x equals 1 over 1 minus x squared. I know some of you know where this might be leading towards and how you might approach this problem, but I'm going to show you a non-efficient way of doing this one, but that it works as well. This is the same thing as 1 over 1 minus x times 1 over 1 minus x. And we know what 1 over 1 minus x is, right? So in other words, this, and we wanted to say, we just want to expand this out to find let's find the first 4 terms. Okay. So I know that this is 1 plus x squared plus x cubed plus dot, 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 times 1 plus x squared plus x cubed plus dot, dot, dot. This is true. I can expand each of them separately from each other. And then I can multiply them back in. So I'm moving into the world of series, of infinite series, and then that's where I'm going to do my mathematics to know where I'm going to be at. I'm going to multiply the 1 out first from over here, which would give me 1 plus x squared plus x cubed plus dot, dot, dot. And then I will multiply out the x to all the terms, which is going to give me plus x squared plus x cubed plus x to the 4th plus dot, dot, dot. Then I'll multiply the x squared to all the terms. That's going to give me plus x squared plus x cubed plus x to the 4th plus x to the 5th plus dot, dot, dot. Then I'll do with the x cubed, I'm going to expand with the x cubed, which is going to give me plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th plus dot, dot, dot. And you can kind of see the pattern here. And now I can just add them all together. How many 1s do I have? I just have a 1 plus how many x's? 2. Plus how many x cubes?
3.
Plus how many x to the 4th will I have? 4x cubes plus dot, 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 dot. Because I said only I wanted to find the first 4 terms. Which in retrospect also is the same thing as the series from n equals 0 to infinity of n plus 1 x to the n. Yes? Which is also the same thing that I can shift it from n equals 1 to infinity of n times x to the n minus 1. They're the same, they're equivalent, right? Ooh, that looks like something, right? What does that look like? It looks like the power rule of derivatives, which is another way that we're going to manipulate this series one more time. Let me zoom out right there. I'll pause for some questions. So we talked about the idea that if we substitute a polynomial into a known power series, we're just going to get that, we can just substitute it right in. If we multiply two known series, that's also going to be working as well. And now we can talk about differentiation, that you can now utilize the property of differentiation and integration on a power series, and you still get the same work. So, if you want to integrate a function and you're having trouble integrating that function, you can instead turn it into its power series and do the integration there. And that's where things come a little bit more interesting. And that's where I said, like, you have the integral. And do I have time? I don't think I'm going to have time. Of like e to the negative x squared, and you try to integrate that, which is something that's unintegratable, but you can figure out its Maclaurin series, then plug in negative x squared, and then you can do the integration on each term, and you can calculate the value. Or you can calculate what the error is going to be as well. Hey, don't do that. Okay, I guess I got 10 minutes until this whole thing goes kaput. Differentiation. Of Maclaurins. Now, I only have time in this lecture to do only all this work with 1 over 1 minus x, but everything holds true for the other 3 Maclaurin series that you'll need to know as well, which I'll put at towards the end of this lecture. So differentiation means that the derivative of is the, well, let me just do the example. We can also take the derivative to find some stuff that we know. So when I had f of x equals 1 over 1 minus x quantity squared, we can also recognize that this is the same thing as the derivative of which function? 1 over 1 minus x quantity squared is of 1 over 1 minus x. If I take the derivative of 1 over 1 minus x, I get positive, or no, because times negative 1. If it was 1 plus x on the bottom, then I would get the negative. But the negative 1 comes down, then times the negative 1 from the chain rule gives me back to what we have here. Okay? So, we know 1 over 1 minus x is 1 plus x squared plus x cubed plus dot, 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 plus x to the n. And now we know that 1 over 1 minus x squared is the derivative of 1 over 1 minus x, which would be 0 plus 1 plus 2x plus dot, 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 plus n times x to the n minus 1. Which is the same thing as the series from n equals, but it's not from n equals 0. Because we took the derivative of the 0th term. So this series starts at n equals 1 to infinity of n times x to the n minus 1. So so they are the same thing. So if you were to do it this method, you would get the series in terms of from n equals 0 to infinity. But if you're using differentiation, you're actually going to be starting at n equals 1, not at n equals 0. So that's just something just to note in there. It's the same, they're equivalent, they are the same thing. And that's also why it started at 1 and not 0. Integration. Let's say we want to do f of x equals 1 over, or sorry, not 1 over, the natural log, well, let's say we wanted to do arctan of x, okay? We could do the derivative, the second derivative, the third derivative. It gets ugly very fast. But we know that this function, the arctangent of x, is the equivalent of what? The integral of 1 over 1 plus x squared dx. Wait a minute, didn't we just earlier in this lecture figure out 1 over 1 plus x squared? So we found 1 over 1 minus x. So right, we did 1 over 1 minus x was 1 plus x squared plus dot, dot, dot. We figured out 1 over 1 plus x squared gave me, what's it? 1 minus x squared plus x to the 4 minus x to the 6, oh yeah, plus x to the n, plus negative 1 to the n, x to the 2n. And so now we can do arctan, which is the integral of 1 over 1 plus x squared dx, which is equal to the constant plus, right? Instead of saying the indefinite integral, I'm going to put the constant up front. And then we can integrate. So I get x minus x cubed over 3 plus x to the fifth over fifth plus dot, 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 plus negative 1 to the n over 2n plus 1 times x to the 2n plus 1. How do I figure out what the constant is? The constant is just equal to what? The first term. Arctan of 0, which is? It's 0. Tangent of 0 is 0. Tangent of pi over 4 would give you 1. So we now know that arctan can be expanded as, so arctan of x is equal to x minus x cubed over 3 plus x to the fifth over 5 plus dot, 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 plus negative 1 to the n over 2n plus 1 times x to the 2n plus 1. Oh, do we have time? Do we have time? I got 8 minutes. All right, there are ways to do centering at x equals a. I just don't have time for that part of the lecture. It's fun stuff, too. No. So, we're not done. I'm just saying I'm going to skip the part about that one. So, I think I got to look at the practice final questions I had. There might be something I want to find the known, using manipulate it at x equals 1 or x equals 2. That part won't be on the final. Other, so, known Maclaurin series. So, we're not going to do them all the way out. So we know the first one, 1 over 1 minus x, is 1 plus x squared plus x cubed plus dot, 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 plus x to the n. That should be memorized. The other one that is memorized, that is very straightforward, is e to the x. E to the x is, and if we did the work out, you would do the same thing. I could do the whole kind of lecture with just e to the x. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 plus x to the n over n factorial. Okay. Sine of x. What is the sine of 0? So that's going to give me, the first term would be 0. So the first term would give me x. And it looks like e to the x, so minus, that's the first power. So minus x cubed over 3 factorial. Skipping 1 every single time. X to the fifth over 5 factorial. Minus x to the seventh over 7 factorial. Plus dot, dot, dot. Plus negative 1 to the n times x to the 2n plus 1. All over the quantity 2n plus 1. Factorial. And cosine of x, cosine of 0 is? What is it? What's wrong?
1 minus x.
Because you're starting at 0. 0 plus 1? Correct. So when you plug in 1, you get 2 times 1 plus 1, which is 3. Okay. Which is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial plus dot, 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 plus negative 1 to the n times x to the 2n over 2n quantity factorial. I like this proof just a little too much. I'm not going to go into, I'm going to show you really quickly because I want to show you the next two things. The next thing is just something that's really cool that shows you why using these properties of series can prove some pretty cool stuff. So this is just like a this is just a proof of something that we know, and that's e to the I0, e to the I theta. E to the I theta, if we use the same expansion that we just learned, knowing its known Maclaurin series, would be 1 plus I theta plus I theta squared over 2 factorial plus I theta quantity cubed over 3 factorial plus dot, dot, dot. Yes? So, I'm kind of going to do this quite quickly. This gives me 1 plus I theta minus theta squared over 2 factorial minus I theta cubed over 3 factorial plus theta to the 4th over 4 factorial plus dot, dot, dot. Yes, because I to the, now remember I squared is negative 1, and I to the 4th is just positive 1, which is the same thing as 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial plus dot, 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 plus I times theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial plus dot, dot, dot. Yes? This is the same thing as cosine theta plus this over here is the same thing as I times sine theta. And this is where you get that amazing property that if you've taken that e to the I theta is equal to cosine of theta plus I sine of theta, which is cool on its own. But now, if we plug in theta equals pi, you get e to the I pi equals cosine of pi plus I sine of pi. Sine of pi is 0. Cosine is negative 1. E to the I pi must always be equal to negative 1. That's where it comes from. Huh? Yeah. Euler. More Euler, right? I want to just end up doing one more example of a type of problem that I would give you on the final exam. One more. It will be, but not in this course. No, not Friday. That's just a proof. That's just for, it's a fun property because I want you to understand why you're doing what you're doing, why these series become so important, why you can change the plane of mathematics and do the world. A lot of it has to do with series. Yes?
Did IPX ever cover that kind of that we just said, that you just did?
It's literally just coming from what we just did right here of showing sine of x.
But like they did that.
Oh yeah, it's something that we don't use in our course, but it's something that you will use like in differential equations, especially, and you get into higher order mathematics and algebra. It's just a cool property of knowing why this is. All right, the last type of problem that you can get is something like, let's say I have g of x, which is negative x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. And I said, find a formula for g of x. Basically, I'm saying, which function would give us this Maclaurin series? What does it look like? Close. It looks like cosine of x. We know cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And we recognize that. However, it's missing this term right here. So we can subtract 1 from both sides, and therefore g of x is cosine of x minus 1. So this right here is for cosine of x minus 1. You're finding and recognizing what you already have, and you can go that way. It's 11:55. It's been a fun summer. Thank you guys, everybody. I will see you in office hours.